Hello. Just before we get into the stream itself, can I just verify that I'm audible? Test, test. Okay. Well, let's go ahead and get started. So, there's not a lot of information out there for dealing with some of the unique or uncommon issues that arise when trying to model a woodwind instrument, specifically a conical woodwind instrument in CAD. There's a lot of. It's not like a box or a cylinder. Especially if it's a conical woodwind, um, it can be a little bit. Well, there are some tricks I've picked up that I thought I might like to share. So what you see on screen now is what we're going to be remaking in this video. It's a kind of a very simple model of a woodwind. There's only two tone holes, and it's pretty short, but the principles we talk about will be applicable to almost anything. And I'm going to have to apologize in advance. I'm going to try to make this stream somewhat fathomable to people who maybe don't have a lot of CAD background. So if that means I'm a little verbose at times, I do apologize for those of you that already have CAD experience. Okay, so, well, let's start real quick and talk a little bit about how we can model a so a woodwind, or a conical woodwind, is essentially a truncated cone. So in CAD terms, what that's going to mean, or the option I suggest, is going to be making this sort of quadrilateral and revolving it around an axis. So you get a truncated cone. The other option would be I could start with a circle and extrude that out with an angle. But personally, I'm not a big fan of that approach, just from experience. So, let's start a new file. Actually, before we do that, let's take a little bit closer look at what we're going to be doing. So my philosophy when dealing with CAD is I like to keep everything very flexible, which means if I were to decide that, for example, this tone hole is too big and I need to make it smaller, or this tone hole is on the is on the wrong axis. I want to be able to fix that without breaking everything and having to start all over from scratch. So this is a demonstration file I made to show you the sort of flexibility I'm talking about. Now, in this demo file, I went a little overkill and made this fancy little graphic, or this an iLogic form, but you can get all this flexibility without having to go through all this trouble. So I can change almost everything about this without breaking the file, which when you're dealing with, especially when you're dealing with a prototype, is very important. You know, like with the Sopranoon I worked on, I wouldn't have, you know, I ended up doing like 6 revisions of that instrument. If I had to remake the file every single time, it would have become pretty prohibitive. So if we just look at the kind of the basic bore of the instrument, I can modify the length, the truncation, the taper, and the wall thickness, and the file itself, the model itself, still works. And I'm doing that by using parameters. If you're dealing with a CAD program that has parameters, they're a very powerful tool. And I'll, just to make a really easy or a really simple version to demonstrate how you can use parameters. So let's say I'm making a box. So I'm going to draw a rectangle and I'm going to extrude it up. So I have a box. Now I can go in and specify all of these dimensions. So let's say 30 millimeters by 20, and make that 10 millimeters tall. So I've hard-coded all of these dimensions into the file. But let's say that I didn't know exactly what size the box would be, but I knew that it needed to be in these proportions. So 1 by 2 by 3. So what I could do is, instead of typing in dimensions, I can type in parameters that I have defined. So here in Inventor, if I switch from the 3D Model tab to the Manage tab, I can pull up the parameters, and I can add a numeric parameter. So I'm just going to call this one, let's say, box height, and set that to be 10 millimeters. Let's say box width, 20 millimeters, and box length, 30 millimeters. It's a little hard to see. There's also this dialog for unit type. By default, it will be the default units of your file, either inches or millimeters. But for some parameters, you'll need to change that. So, for example, you might want to need to change it to degrees, or UL. That's Inventor's fancy way of saying unitless dimension. So if it's just a ratio. But we'll get into that later. Okay, so now when I'm defining this rectangle, instead of 30, I'm going to just type box length, because I have defined that parameter, and then box width, and the height I'll just set to box height. Okay. But the real power of these parameters comes when you define the parameters in terms of other parameters. So once again, in the scenario where we know all of these dimensions need to be in the same proportion, instead of saying box width is 20 millimeters, I'm going to say that box width is box height times 2, and that box length is box height times 3. So now, whatever I change box height to, the rest of the model will adapt accordingly. Now, you might ask, well, couldn't you just achieve the same thing by scaling the whole model by a certain amount? Yes, but let's say that, for instance, we have another feature. Let's call it a shell. So here, I've made this box hollow with a 5 millimeter wall thickness. So now, when I change, if I were to scale this entire model, the wall thickness would change with it. But since I've have my my wall thickness set independently from the rest of my parameters, I can change the box size while keeping the wall consistent. So this just gives you a lot of power over making some things flexible and some things fixed. Okay, so let's close that. And let's finally get started on our conical woodwind. So first thing we're going to do is start a sketch. We're going to need to specify a work plane. I personally like to mainly start with the XZ plane. That way, the long axis is the Z axis. It just makes things a little bit easier if you're going to be 3D printing. And I'm going to draw this little quadrilateral that we are going to rotate around the Z axis to produce the bore of the instrument. So now, one thing I like to do with conical woodwinds is make the origin of the model, so this point right here, make it the apex of the cone. So, and I did that by setting a coincident constraint from the kind of this hypotenuse to this imaginary point. That way, when you set a length, you're setting the length, the acoustic length of the instrument rather than the physical length of the instrument. That just kind of makes things a little bit simpler overall for me. Okay. So let's open up our parameters and create some parameters. So one thing we're going to need to know is the overall length. And, or I guess just to clarify, I'm going to call this the acoustic length. Normally I wouldn't be so verbose, but since since this is going to be part of a stream, I'm going to make these parameter names a little bit longer than I normally would. And then we're going to add, okay, well, we'll start with that. And just for simplicity's sake, let's say that's 500 millimeters. And now I've set this, use this parameter to define the overall length of the instrument from the bell of the instrument to the apex of this imaginary cone. But we can still move this. So we need to constrain that. And I'm going to create a new parameter, truncation length. And let's just set this to 100. So in a conical woodwind, this would be the missing part of the instrument. So the if we were to imagine that this bocal continued all the way to an imaginary point, it would be the length of that point. The volume of that missing part of the cone is what the reed has to acoustically take care of or compensate for. Okay, so right now we have most of the things, information we need. The only flexibility we have left is the radius of the instrument, the scale of the instrument. And there's a lot of different ways that you could define this. You could set it to an angle. So like, let's say 8 degrees. You could define the bell diameter of, let's say, 50 millimeters. You could define the aperture diameter, let's say 4. Sorry, I keep on saying diameter, I mean radius. Personally, what I like to do is define the taper of the instrument. So if you imagine a line, a taper is like a slope. It's not an angle, it's just saying that for every 1 millimeter in length, you are getting, let's say, 0.05 millimeters larger in diameter. And this comes in handy when you're dealing with tone holes, because it gives you a very easy way to figure out the bore radius at any given tone hole position. So if I were to define this as an angle, then in order to figure out the length of this line here, I'd have to do some trigonometry, which isn't a big deal, but it's a lot easier if I know my taper, and I can just multiply the taper by the position, and that will get me the radius automatically, or well, more easily than with the angle. So I'm going to define one more variable, or one more parameter. I'm going to call it taper. And here we actually do need to change the unit type to unitless, since this is millimeters over millimeters, which cancel out. And I'm going to say 0.05. So back to my sketch. Instead of setting this to 50 millimeters or something like that, I'm just going to say that the radius of the bell is equal to the acoustic length of the instrument multiplied by the taper. So we end up with 25 millimeters. And now our quadrilateral is fully constrained, and we can revolve that around the z-axis and get a model of the bore of our instrument. And if we need to change anything, we can just go back to our parameters. And for example, make it shorter. Make the truncation longer. Why? Oh, I didn't actually set that in the sketch. Or to make the taper wider. And if we're careful with the way that we do the rest of the components, we should be able to change that even after we've done a lot more work on the instrument, which comes in really handy. Okay, let me, have to change that from a hard-coded dimension to the parameter we set up, the truncation length. Okay, so right now this is a model of the air column, but for the actual instrument, of course, we need one more piece of information, which is the wall thickness. So open up our parameters again and add one more parameter called wall thickness, and I'm going to set that to 6.5 millimeters just because it's what I use for the subcontra bassoon. And let's go back to our sketch and add this extra little quadrilateral to represent the wall. So I'm going to set these sides to be vertical, and I'm going to set these two lines to be parallel, so I'm using these constraints. So now the only thing we need is the dimension. Now we already know the dimension we want to use, 6.5 millimeters, but there's actually two different ways that we could define the wall thickness. So we could, for example, say that our wall thickness is the distance between those two lines. The perpendicular distance between those two lines. But as a consequence, that means that the cross-sectional wall distance or thickness is going to be very slightly different. So we have 6.5 millimeters here, perpendicular, and 6.508 millimeters for the cross-section. If we imagine that the taper was a bit wider, then these dimensions get even further apart. So now we have 6.5 and 6.7. Or multiply the taper by 20, and all of a sudden our wall thickness is 9. Our wall thickness is 6.5 by one reckoning and 9.2 by another. It doesn't really matter how you define the wall thickness, whether you define it as the perpendicular distance between these two lines or by the cross-sectional distance by this line. For woodwinds, you're mainly dealing with pretty shallow angles, so the difference between these two definitions aren't going to be terribly great, but you do need to be consistent. Otherwise, you're going to end up with parts that don't quite align. I personally like to define my wall thickness by the wall thickness of the cross-section, which means anytime I take a cross-section of the instrument, the 2D cross-section will have a wall thickness of 6.5. it means that the perpendicular wall thickness is slightly less, 6.492. But if it's too small, I can always just increase the size of the wall thickness parameter. Okay. Now we could, let's hide that. So if we go back to our sketch, we could just revolve this profile around our axis. And get, oh, hold on, sorry. And get the bore of the instrument, or sorry, the actual geometry of the instrument, hollow on the inside. But I like to do things slightly differently. Let's just delete that. So I like to make two different solid bodies. One to define the inner bore of the instrument. You can ignore these kind of weird tumors for now. Those are part of the tone holes. As well as a exterior of the instrument, with a solid that's solid on the inside, and then subtract those two from one another towards the end. It makes things a little bit easier. For example, if you're needing to make a riser on the instrument or a riser on one of the tone holes, to be able to work with the exterior and the interior of the instrument independently. So in order to do that, I'm going to go back to, I'm going to create another revolution using the same sketch. And this time, instead of selecting just the interior, I'm going to select the interior and the wall. Rotate that around the z-axis, and I'll have the exterior. And one other thing, if we see output, there's a couple of different options. There's join, which means this second solid that it's creating, it's going to join it to the solids that already exist. Cut, which is where it's going to use it's going to use this new solid to subtract from the solid that already exists. Interference, or intersection, is going to be the intersection of these two solids. But what I actually want to do is create a new solid, this last box here. So now we have two entirely independent solids, one for the interior of the instrument and one for the exterior of the instrument. And once again, we can go in our parameters and change anything we'd like. So we could have a 20 millimeter wall thickness, or a 0.01 taper. Okay, so so that's the exterior of the instrument. Let's talk a little bit about the tone holes that we're going to be adding. What sort of parameters we want to be able to use, or that we want to be able to change. This is for a woodwind instrument. This is for a prototype of a woodwind instrument. This is really critical. Being able to easily change tone hole parameters. So some of the things I do may look overly complicated, but it gives you that flexibility, and it makes it less likely that the entire model breaks when you change something. So I'm going to go back to our form, and we can look at some of these parameters that I've defined for the tone holes. So first of all, I've defined these 4 parameters as common to all tone holes. Let me actually, I'm going to set up a cutaway view so we can more easily see what I'm talking about here. So the face angle is so normally on a woodwind instrument, the tone holes are faced so that they're only coming into contact with the pad for a small area. You wouldn't really want the pad to have to come on a perfectly flat surface, on a large perfectly flat surface, because then it's going to be really difficult to seal. So I could set this angle very shallow or pretty steep. Next we have what I'm calling the relief angle, which is this angle here. Now, on a lot of woodwinds, the relief angle would be almost perpendicular, essentially 0. However, with 3D printing, it produces a lot less overhangs if you add a relief in like this, so that when you're printing this upright, this surface isn't floating in midair. It just saves you a lot of trouble, and you don't have to deal with very many supports. So I usually set this on 45 since I usually work in ABS. If you were printing in PLA, you could probably set this something more like 30 or even 20, 25, and without too much trouble. And if you were modeling an instrument that was going to be made on a lathe, you could set this in 0. Next up we have the rim. This is pretty minor. This is just the thickness of the portion of the tone hole face that is flat. Especially if you're 3D printing, you don't want to make this like a knife's edge. You want there to be a little bit of flat surface. And then finally, we have the riser wall thickness. So if this tone hole were long enough to need a riser, then the riser wall would define how thick that is. So these are the 4 parameters that are common to all of the tone holes. So I'm going to go ahead and add those into the file that we're making right now. So let's see, tone hole face angle, tone hole relief angle. This is going to expose some of my bad typing. Tone hole rim, and tone hole riser wall thickness. Now for the face angle and the relief angle, we have to change the unit type to degrees, tone hole rim and tone hole wall thickness are going to be millimeters. So for now, I'm just going to set these at values I like to use. So 8 degrees for the face angle, 45 degrees for the relief angle, 0.5 for the rim, and 4.5 for the riser wall thickness. Okay. So now we have the parameters that we're going to need to define for each tone hole. So position is the position of the tone hole, where 0 is the apex of the cone. So if I set it to 0, we get a pretty nonsensical tone hole that's not even on the physical body of the instrument. But it's very common that when you're dealing with prototypes, you might need to say, that needs to be 235, or, oh, that's a little too flat, so 227.5. So we definitely want to be able to change the position. The radius is the size of the tone hole. The length is the length of the tone hole. So if it's, and the way that we've done this, or the way that we're going to do this, if the length is longer than the wall thickness, it's going to automatically generate a riser. Now, of course, we could go really overkill and put in some logic that detects, for example, if we try to set the length too low, we're actually going to be cutting into the instrument and making an extra hole. But as long as everything's flexible, we can fix any errors like that occur pretty easily. The pad overhang is the size of the pad, or the way that I've defined it is that 8 millimeters, well, let's set it to 0.5. This means that the radius of the pad is 0.5 millimeters larger than the radius of the tone hole. If I make that larger, the pad is larger, and that means that the facing for the tone hole has to be larger to accommodate the pad. Obviously, the pad has to be able to fit down in this facing. Now, if you're making a large instrument that's going to be keyed, well, let me back up a little bit. So this next parameter you're not going to need if you are making a large instrument that's going to be keyed, and that is the angle of the tone hole. So right now, I can angle this tone hole so that it's forward or backwards, which is sometimes necessary if you're dealing with if you're positioning tone holes to be played by the human hand directly. You will need probably to angle some tone holes. So just for the sake of this project, we're going to go ahead and program that in, even though you will not need it for every tone hole. And I guess I should say, For some tone holes, you won't need, for example, a facing at all. If you're going to be playing it by directly by the finger, then you can just use it. You don't need a facing, and we can do that by simply suppressing some of these features after we've made the rest of the file. Personally, I like to err on the side of having extra flexibility, even if I don't think I'll be needing it, just because I've had it happen too many times where, oh, I'm not going to need to angle this tone hole, I'm just going to skip that step. And then sure enough, like a month later, I need to angle this tone hole, which means I have to dig back to the beginning of the file, rework everything of how I made that tone hole, and then fix the multiple errors that pop up because things were created in reference to geometry that's no longer there. So we are going to be defining that angle, but we don't need to. But for some sorts of instruments, you can skip that step. And the last parameter I have listed is what I'm calling roll, which is just the radial position of the tone hole. So -70 means it's rotated 70 degrees. The entire tone hole is rotated 70 degrees around. Okay, so let's go back to the file we're working on, and we'll add in those parameters. So tone hole 1 position, tone hole 1 radius, tone hole 1 length, tone hole 1 pad radius, pad overhang. If you set the pad radius separately, it can create. It makes things a little bit messy. If, for example, you accidentally change your radius of the tone hole before you change the radius of the pad, and then like if temporarily the pad is smaller than the tone hole, some stuff can go wrong. So pad overhang, tone hole 1 angle, and tone hole 1 roll. And the stream's going a little bit longer, so I think we're just going to do one tone hole for this file. But the same principles will apply for any of the others. Actually, I take that back. Let's real quick. I just thought of something. I'm just going to add the parameters for tone hole 2. Tone hole 2 angle, tone hole 2 roll, and there's one more that I'll talk about in a second. Okay, so now we have all of our tone hole parameters, and we'll just make some stuff up. So our positions for our tone holes, let's say, is 220 and 350. The radius of the tone holes, let's say, is 3 and 6. Length of the tone holes, I'll say 4.5 and 8. Pad overhang, I'm going to set both of them equal to 4. So that means that the pad is the diameter of the pad is going to be 8 millimeters larger than the diameter of the tone hole. Okay, and for the angles, we need to change our units to degrees. So here in the unit type, I could try to figure out where on earth degrees are in this drop down thing. I guess that here, angularity, and click on that. But you can also just type in degrees. So let's say our angles are -10 and 10, and our rolls are, let's say, 20 and -20. Okay, so we've done the kind of the boring parameter stuff. Everything should be set. Now we just need to start creating this geometry. So let's start with, so the first thing we want to do is create the tone holes and the risers for the tone holes. And I'm going to do this by creating a new sketch on the YZ plane. Now, the temptation would be to go in and project all of this geometry from the existing solids. So now when we're looking at this, we have the wall and the bore. Personally, though, whenever you have these projected geometries and then try to go back and try to change things or update things after the fact, there's a lot of stuff that can go wrong, and you end up with files that need a lot of babysitting whenever you need to change something, or at least that's my experience. So I'm actually not going to define anything using the solids that already exist. I'm going to define everything from the origin. So we already have our origin here. I'm also going to define this XZ axis. And now we have all the information we need to create our tone holes. One thing I'm going to change real quick is this axis projection. I'm going to change that to a construction line. If you've never used construction lines, they are wonderfully useful. Here, I'm going to show what I mean real quick because it's something I didn't know about for way too long. So let's say that we have, so I'm just opening a new sketch just to demonstrate something. So we have this circle here, and we need it to be in relationship to this line here. So let's say it's 5 millimeters offset from this line. Okay, so we finish that sketch and we go to extrude that shape. So now we have two profiles, the circle and the line. And the line divides the circle in two. So we could, for example, select both profiles. But if something were to be updated so this line no longer fully divides this circle, things break because you're now missing one of the two profiles that you extruded. If, on the other hand, we go back and we set this line to a construction line, so here it's in the format, that means that it's a line that's only used as reference, not to create profiles. So now if we go and extrude that, we can only select the full circle. In choosing profiles, it's ignoring this reference line. And that just makes things a good deal more robust if you need to change things. Any line that doesn't need to be part of the profile, set it to construction line. Okay, so here we have one of our tone holes. And I'm going to use a revolution to create this tone hole. So I'm going to be drawing a rectangle and then rotating it around an axis rather than drawing a circle and extruding it. It's more of a matter of preference, but it's my preference, and it's the one I think overall works better. Okay, so here's our tone hole. This line here is the center line of the tone hole. So I'm going to set this distance to tone hole 1 position. And let's go ahead and create our second tone hole. Tone hole 2 position. Okay. So we have our 2 tone holes. We also need to set the radius. Tone hole 1 radius. Tone hole 2 radius. Okay. So we have the basic information we need. You might notice, however, that it's still purple, or it's still, in the way that I have things set up, if it's purple, that means there's still freedom of movement. Something is not fully constrained. For example, you can see here, if I move that, it was not fully constrained. Generally, it's good practice to keep everything fully constrained. So what I'm missing is a perpendicular constraint here and here, and and let's just add some more perpendicular constraints. Now, a lot of times, Inventor is set up to automatically create these perpendicular constraints. I have that turned off right now. I find that it's more trouble than it's worth. You know, you'll make a sketch, and then all of a sudden you'll find that this line has been automatically made perpendicular to this line, or automatically made parallel. So you have to go in and manually delete constraints. I find it easier to just manually add the constraints I need rather than having to go back and delete constraints I didn't want. So the only thing we're missing now is the length of these tone holes, but we're actually not going to set that here. So this is just going to be, we're not modeling the instrument here, we're modeling the hole. So it doesn't matter how long we make the hole, as long as the hole is longer than the instrument could possibly need. So what I'm going to do is I'm just going to say, let's say, let's say, acoustic length times taper times 2. So that's 2 times the bell radius. safely larger than we could need it. And actually, I'm going to bump that up to 3. And then here, I'm just going to set that to the same thing. So it just needs to be larger than it could ever need to be. Okay. Now there's one more thing we're going to add in this step, and it's a little complicated to describe why, but I'm going to add this little construction line here. And we'll come back to what it does later. But I'm going to have the beginning of this construction line. Okay. So the beginning of this construction line, is how we're going to define the axis that we rotate the tone hole by. So if we go back to our demonstration file, modify, let's unroll, okay. Okay, there we go. So when we rotate, or when we set the angle of this tone hole, we don't want to set the angle, we don't want it to rotate from the center of the bore, because that would mean that we're drastically changing the position of the tone hole when we change the angle. So you can imagine if the tone hole was rotating from the center and we rotated it by 45 degrees, we would be a good, 10 millimeters further along the bore. So instead, we're rotating it from a point where the center of the tone hole intersects with the wall of the bore. So when I rotate this, you might be able to notice we're rotating from a point right about here. So in our new file, that's what we're setting now. So we need to set this position to the wall of the bore at that point. Now, since we define this by taper, we can actually do that numerically very easily rather than needing to, for example, project this wall here. So I'm just going to multiply or take tone hole position 1, tone hole 1 position, multiply that by the taper. And we've that's in the correct spot. So if we show our bore solid, we can see that that is the right point. The only difference is we haven't had to project anything, which once again, in my experience, just means there's a lot more things that can go wrong whenever you try to update things. So here I'm going to set this to tone hole 2 position multiplied by the taper. And there we go. Now that's one end of the point. The other, sorry, I hit the mic. The other end of the point is where we are going to be creating the tone hole facing at. So you might notice here, when we angle the tone hole, we normally wouldn't want to angle the facing, right? You wouldn't want the pad to have to come in at some weird angle to match the angle of the tone hole. You want the pad to be perpendicular to the body of the instrument. So in order to do that, we are going to set this angle at our tone hole. We're going to set this angle to our tone hole angle. And in order to do that, we're going to say 90 plus tone hole 1 angle. So since we have this angle set at -10, it takes 90, subtracts 10, and equals 80. You might wonder why we can't set this angle instead, so we don't have to subtract it from 90. Well, it's red, and it's going to say this expression evaluates out of the expected range. That's because it's a negative number. This dimension is scalar. It's not vector. It doesn't care which direction it is, which means it cannot accept a negative value. So to solve that, I'm setting the angle from this line down here and subtracting it from 90. Okay. Do the same thing for this angle. 90 plus tone hole 2 angle. Okay. And then the final thing we want to know is this is where we're going to set the length of this tone hole. So tone hole 1 length, and then tone hole 2 length. One important thing to notice here, there are, by default, the dimension it wants to create is orthogonal to the reference plane. So here, the dimension it wanted to automatically create was 4.5 millimeters straight along the y-axis. But that's not what we want. We want this line to actually be 4.5 millimeters long. So we have to kind of click it once to start the dimension, and then click it a second time to change it so that it's measuring along the line rather than along the y-axis. Okay, so there's our tone holes. One more thing we're going to do in this step is we're going to create the risers. Now, some of these tone holes aren't going to need risers. They're short enough. But once again, I find it better to model the riser, and then if it doesn't need it, it will automatically, the steps we'll do later automatically get rid of it. Rather than thinking you don't need a riser and then having to go through and manually change everything. So this is just another rectangle on the outside of the tone hole. So for this width, we're going to say tone hole riser wall thickness. That parameter we already set, only typed correctly. Tone hole 2 or tone hole riser wall thickness, and let's make sure this is all fully constrained. Once again, your Inventor probably does this automatically, but I find it easier if it doesn't. Oh, where did that go? Okay. And then I'm just going to do one last perpendicular constraint here. And perpendicular constraint there. Okay, so everything's perpendicular. Now we just need to set the length. This is, once again, the actual length that we set here isn't terribly important. It just needs to be larger than it needs, or it needs to be longer than it's going to be, but not longer than this tone hole. So here I'm just going to say that, well, here, we'll just make things simple. Say that this is 80. Nope. 40. Okay. Okay. So now let's create our tone holes. So I'm going to revolve. So tone hole 1. Select the profile. We're going to rotate it around the axis that defines its position, and make sure that it's creating a new solid rather than merging with one of the solids we already have. And that will be everything we need for this tone hole. Now, instead of clicking OK, I'm going to click this little plus, which will, well, here, I'll show you. If I click OK, it automatically hides this sketch and assumes that you're going on to do something else. We're actually going to, instead of clicking OK, I'm going to click this Apply and Create, which is going to keep this sketch open and allow me to create multiple sketches from, or multiple solids from the same sketch. If you accidentally skip this step, you can undo it, and but it's just easier. Less time spent in dialog boxes if you click the plus rather than OK. Okay, so we have our tone hole, our solids that will be defining our tone holes. Now our solids that will be defining our risers. So we're going to be using that same axis. And then, so there we go. We have our tone holes and our risers. Okay, I'm going to name these real quick. So bore, body, tone hole 1, tone hole 2, riser 1, riser 2. Okay, Mark, we're creating just a sample conical woodwind in Inventor, kind of just going over the method I used for kind of maximum flexibility and general not breakingness. Okay, so we have our solids. The next thing we want to do is we want to angle all 4 of these solids by the tone hole angle that we have defined. And to do that, we're going to need to define an axis of rotation. So I'm going to hide all of these solid bodies and make sketch 2, or make the tone hole sketch visible again. And we're going to create an axis through this point. So to do that, I'm going to make the plane that this axis was on visible. And over here on Work Features, if I click this drop-down box next to Axis, there's an option for Normal to Plane through Point. So we want to create a plane, an axis that's normal to the sketch plane through this point right here. And that's going to be our rotation axis for the tone hole. So just click that, the plane, and the axis. or the plane and the point, and now we have that axis that we're going to be rotating our tone hole by. Do the same thing for the other tone hole. So click the plane, click the point. So now we have our two axes. We can hide that sketch and bring back our solid bodies. So now we want to rotate these tone holes and risers. So to do that, we're going to use, if we go to the Modify menu, there's this tool called Move Bodies. Let's hide this plane. Move Bodies. So by default, it's in drag mode, which means we are moving these bodies linearly. That's not what we want. We want to rotate about this line. So click on the tone hole body, and you see it's outlined in yellow. Now, for our angle, we're going to say tone hole 1 angle. We've already defined that parameter. And for our rotation axis, we're going to pick that line we just created. And if we hit apply, we'll see that that tone hole is now angled at the angle we want it to be through this line that we defined. So we're going to do that for the other tone holes as well. Switch the mode to rotate about line. Select the body that we want to rotate. Tone hole 2 angle, and click the line in question and apply. So now let's do that for the risers as well. Click on the body. Okay. Tone hole 1 angle. Rotate axis. Apply. And then click on bodies. Rotation axis, tone hole 2 angle. And real quick, I'm going to change something. You might notice that right now these risers are hollow. I'm going to make them solid just to make things a little bit more straightforward. So I'm going to need to go backwards in the file. I could just edit these revolutions, but once again, put the same category of things that it took me way too long to learn in Inventor. I can just click on one of these features, and I can say Move EOP Marker. EOP stands for End of Part. So if I do that, it's going to kind of go back in time, and I can modify these features as though I hadn't done anything else beyond this. And this is really handy if, for example, you've realized that you needed to do, you did things in kind of the wrong order. So edit this feature and click, well, I just realized I did things a little bit. Okay. I did things a little bit differently than I did in the demo file. We'll accept those hollow tone holes. It's not actually going to create a problem. Sorry, those hollow risers. Okay. So now we want to make our facings. So let's go back to or sorry, I should actually describe what I'm doing instead of just doing it. We're going to create a new sketch, once again on our YZ plane. And these solids are going to define our facings. So this kind of impression here. So let's hide all of these solid bodies, and we're going to project our Z-axis again, make it a construction line, and we're also going to project two things from sketch 2. So if I right click on sketch 2, I can select visibility, or just type V, and I can show sketch 2, and I can use that for getting information from an earlier sketch and a later sketch. And the only thing I need is this point here, because this point is going to be the center of our facing, because it's the center of the exterior of the hole after we have rotated the hole. So project that point, and project that point from our tone hole sketch, and now we can turn off visibility, and there we go. Okay. So for our facing, we are going to use this. Well, I'm just going to make this shape, and then I will describe why. So get everything perpendicular that needs to be perpendicular. Okay. So here we have this very bizarre shape with that point that we defined as its center. So we are going to be rotating these profiles around this axis here to create the facings we need. So this distance is going to be the diameter of the tone hole plus the diameter, or the rim. So if I just type tone hole 1 radius plus tone hole rim, we've now set it to 3.5. Actually here, I think that there's a way to do this where you can actually follow what. Okay. Okay. So this is what we're going to be creating, kind of a reverse of the facing we want. So that's going to make it just a little bit larger, or the center part of this facing just a little bit larger than the tone hole will be. And then we want this angle to be our face angle that we have previously set. Tone hole face angle So now it's 8 degrees. Okay. Now this is going to be the size of the facing. So we need to set this large enough for the pad with a little bit of clearance. So I'm going to say tone hole 1 radius plus tone hole 1 pad overhang. So now we have 7. Now that's the exact size of the pad. Practically, we want a little bit of clearance here. So that last parameter I added, tone hole pad clearance, is where I defined how much clearance. So tone hole 1 radius plus tone hole 1 pad overhang plus tone hole pad clearance. Now we have so now it's large enough to fit the pad. Okay, so this line here is going to define our relief. So once again, if you're 3D printing, it's usually handy to have this facing not be perpendicular to the long axis, but to be angled so you don't have to deal with supports. So there we go. Now, this line here, I have set to be collinear with this line. And this is a pretty minor thing, but this is what we're going to use to shorten the risers. Okay, so right now we have a few lines that are still unconstrained. And just like the tone hole solids, these solids don't have to be an exact size. They just need to be larger than you would ever realistically need. So I'm just going to set that to 120. And once again, set this one to larger than it would need to be, so 20. And we have everything we need to create the facings for this tone hole. So for the next tone hole, what I'm going to do is I'm just going to select everything, copy, and paste it. And if everything is constrained fully, the only thing we'll need to do is create a new coincident constraint here and redefine this length. If everything isn't constrained fully, if you copy and paste a sketch and try to drag it somewhere, everything's going to go wrong. Like, here, I'll maybe try to demonstrate what I'm talking about. So let's just get rid of these dimensions and all of these things and show constraints. So delete all of these constraints. So now it's just a whole bunch of dumb lines, and when we try to drag it, or like Inventor just has to pick something to move, and it usually picks exactly the wrong thing to move. So copy and pasting sketches is a wonderful tool. just make sure everything is fully sketched or fully defined and constrained beforehand. Okay. Now we're going to do our revolutions to create our facings. So first of all, let's create the facings itself. So select this profile here, select this axis, and create a new solid. We're going to hit apply. Do the same thing for tone hole 2 and hit apply. All right, so now we have our facings. Next up, I want to do the reliefs. And I want to do these separately. Facing 1, facing 2, well, that that didn't clarify anything. Okay. Hide all of that, make this sketch visible. The reason I'm not just creating one solid for both facings and reliefs, if I were to decide that I don't want a relief for this tone hole, it just makes it easier to turn off or to suppress a relief for a specific tone hole if these solids are separate. Okay, so for the relief, I'm going to select that profile, but the same rotation axis. So it's going to look like that. And then same thing for this tone hole. So name these relief 1, relief 2. Sometime for an example of where so even if I'm 3D printing, for an example of where I might not want a relief, or where I might want something more complicated. So if I need to place posts really close to this tone hole, not having a relief at that point can let me place those posts closer to the tone hole than I would otherwise be able to. So that's why I like to be able to have them separately. And then the last thing we're going to do is one more revolution, selecting all 3 profiles. And this is what we're going to use to cut the risers. Riser relief 1. Riser relief 2. Okay. So now we have most of our solid, or all of our solids. It isn't immediately apparent how this helps us, but hopefully it should be in time. Okay, so I'm going to hide all of these bodies except riser 1 and relief 1. Or not, sorry, riser 1 and riser relief 1. And I'll go ahead and, no, that doesn't help. Okay. So I want to use the riser relief solid to remove material from the riser. So to do that, I'm going to use the combine tool. So it's going to ask for multiple solids. So I'm going to select as my base body the riser, the tool body, the riser relief, and then change the output from join to cut. So that's going to subtract one from the other. So now, wait. Okay, I see. Okay. 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 So now our riser isn't overly long. Now this one is actually, this tone hole isn't large enough to need a riser. So it's actually going to be removed entirely. That's why it looks weird, because the tone hole is being rotated from not the position we would want it to be. Or, yeah. So, anyway. Another thing in the category of things that took me too long to learn. So if we go back to our combine tool, if for some reason you need to use this tone or this solid multiple times as a tool body, so let's say you had multiple solids that you need to cut using this riser relief tool body, you can select this option here to keep tool bodies. Otherwise, it deletes the tool body. We don't need this tool for anything else, so I'm not going to have that selected. Okay, so the next option is so we're going to do the same thing for riser 2. Select our tool body, or sorry, select our base body, our tool body, and then set it to cut. And here we go. So now we have our body of the instrument. Okay, so let's worry about the various parts that will define the tone hole. Something seems to be not right here. Why? Oh, I know what it did. Let's see. Hold on. Sorry. Technical difficulties. So I had tone hole 1 set to -10. Okay. So what's happening is these tone holes are being rotated in the wrong angle, or sorry, the wrong direction. So I'm just going to go back to edit feature and click this flip button. There we go. Flip that, flip that. Okay, so now our tone holes intersect with our facings the way that we expect them to. Our angled tone holes with our perpendicular facings. Okay, got that fixed. So let's merge. So we're going to use a combine again, and we're going to combine our tone hole with our facing and our relief, and we're going to keep that on join. So now this is all one solid. Do the same thing for tone hole 2. We're combining these 3 bodies together. And, oh, sorry, these risers are now rotating in the wrong direction. So we need to flip the axis. There we go. Okay. So now that these, the tone hole, the facing, and the relief are all one body, now we're going to take care of that one last aspect of the tone hole, which is the roll. So the position of the radial position of the tone hole. So let's go back to our move bodies option, our rotate about line. So select this body, our tone hole 1 body. Then for our rotation axis, we're going to use the Z axis. And then our direction is going to be tone hole 2 or 1 roll, and hit apply. And then do the same thing for the next one. Apply. Do the same thing for the risers. It is, we can't combine the risers and the tone holes yet because they're going to be used for different things. We're going to add the risers to the body of the instrument, whereas we're going to subtract the tone holes. Okay. And our body is tone hole 1 roll, and our axis is the Z axis. Apply. And then finally, our body here, rotated about the Z axis and by the angle of tone hole 2 roll. Okay. Believe it or not, we are very close. So now we're going to create 2 right now we have 6 bodies. We're going to create 2 bodies. One body for the kind of the positive space, so the solid parts of the instrument, and another body for the negative space. So we're going to combine our body with our 2 risers. Hit OK, and then we're going to combine our bore with our 2 tone holes. Hit OK. So now our body is just the exterior of the instrument plus any riser that we may need. This first tone hole, it turns out, isn't long enough to need a riser. That's why you can't see one. And then this version, or this solid, is the inner bore, the tone holes, and the facings. So that now, if we do one last combine and take our body and subtract from that, or cut from that, our bore and tone holes, we have the finished instrument. Now, this might seem like it was a very unintuitive way to do this. And it was unintuitive, which is why I didn't use this at first. The subcontrabassoon Mark II files are done in a very different way, which was both more difficult and much less flexible. So like if I need to change parts of the subcontrabassoon Mark II files, pretty much everything breaks, which is why as I was doing prototyping for the Sopranoon, I ended up kind of redoing the way that I I do a lot of this. So TechMekhnevek says, when you copied Relief Sketch to Tonehole 2, do I have to change the parameters again manually? I'm not sure what you mean by that. So I didn't copy anything from. I know exactly what you're talking about. Sorry, I don't often do streaming and CAD work at the same time. So yes, that is an excellent point that I should have mentioned. When I copied this sketch, or when I copied the second relief, I forgot to change the parameters. So when you copy and paste a sketch, it by default uses the existing or the parameters from the first sketch. So like right now, I have this sketch set to tonehole 1 radius plus tonehole pad overhang plus tonehole pad clearance. Here, it's just kind of dumbly setting all of those parameters the same. So I do need to go in and say tonehole 2 radius plus tonehole 2 pad overhang plus tonehole tonehole pad clearance. Thank you very much for bringing that up. That would have been a pretty significant oversight. And then for this dimension, I need tonehole 2 radius plus tonehole rim. Now you see, I actually did that on purpose so I could show you all exactly how easy it is to change some of these things after the fact. I'm just kidding. I did not do that on purpose. Okay. There we go. So now, if I want to change anything about this, I can just go to parameters and change these parameters. So let's say all of a sudden I decide I want the taper to be larger. I can change that from 0.05 to 0.1 and we get a much larger taper with everything else staying the same. All of these tone holes are the same length acoustic, or as it would matter acoustically. They're in the same position around the instrument. Now, if you try hard, you can break things. But generally, you're exceeding, in order to do so, you're going kind of beyond the sensible woodwind parameters. So, you know, let's say, for example, I make this tone hole, set the length of this tone hole to something crazy. Like 300. Why did that work? It didn't work. Tone hole 1 length. Did I forget something else? Oh. Yeah, for some reason, was this one right? Yeah? Why was one of them set? Okay, anyway. Yeah, so if I do something crazy like that, I can break it. But for the sort of dimensions you're using for an actual woodwind, this is the kind of the most flexible and robust approach I've found. Now, you may, for example, find that you don't need So let's say, for example, that I was going to be covering this tone hole directly. I can just go through on that feature where I can bind the tone hole and the facing solids. I can just add it. Well, actually, here, what I'll do is suppress that. So suppress the feature. So now I have a simple hole, and I still have the solid for the facing and the relief available if I decide to need it, or if I end up needing it. Anyway, I know this probably has been a little bit, well, I don't know how interesting this stream would be to even the relatively niche audience of my channel, but I'm operating under, I'm sure if you're anything like me, you've tried, or you've had a question and you've searched YouTube and you've found one video with like 12 views that exactly answers the question. So I guess my hope is that this stream might have exactly answered the question for somebody. A lot of the work, the stream took a while because I was needing to kind of walk through the process and describe everything I was doing. In actuality, the process isn't that bad, even for a instrument with like, 15 or so tone holes. So here coming up, what I'd like to do is do maybe a handful of streams doing the same thing, but not for a fake instrument, but for an Altoon, because I really want to fill in the gap between my the Tenorune that I bought and the Sopranoon that I made with a Altoon. So I want to use kind of this method that I talked about here to do that. And I actually do need most of this flexibility for an Altoon. I need, on bassoon, there are even tone holes where it's angled but uses a pad. And there's also tone holes that don't have a facing at all. The only sort of tone holes this sort of, the method I described doesn't really apply for is, so for example, on a bassoon boot joint, you sometimes have these facings that are not, well, these facings that are at an oddball angle, like for the B flat key, you'd have to do that manually. Anyway, I hope the stream has been informative for at least someone, and I really hope I haven't the worst thing I could have done is discourage people from modeling a conical woodwind in CAD. I do think that as unintuitive as it may seem, that this method works quite nicely. If I open up real quick one of the subcontrabassoon body joints, you might be able to see what I'm talking about, how things were done pretty messily. So right now I have, creating the body, that's easy. You know, it's just a sketch rotated around an axis. But to position all these tone holes, I created all of these planes and then created a plane at a right angle to all of these planes, and then used created I projected the bore profile onto these planes at right angles to the planes that I already created in order to define the starting point for some of these holes. It was a huge mess. And if I wanted to go back and change something, there's a good chance I'd have to go back, move my end of part, and then go through feature by feature fixing things. So anyway, if you have any questions, or if there's anything that you think I didn't explain clearly enough, or if there's anything you think that I could have done better, or I'm always looking for ways to kind of improve my process. So if you're a CAD expert and I did something crazy or unnecessarily cumbersome, please let me know in the comments below. One thing I do want to talk about real quick is something I used to do a lot but moved away from that might seem like it would make a lot of sense. So if I go back to my relief, my tone hole relief and facing sketch, I can, for example, instead of, what I did was I rotated this into a solid. One thing is also an option is if I click this button here, I can rotate it into a surface like that. So this is not a solid, this is just a surface. And I can use that surface to cut a part just like I could use a solid. The problem comes if I change anything. So when you have these surfaces and you're using them to cut a solid, the surface has to cut the solid completely. If it doesn't, everything fails. So by doing it as a solid, I guess I should say, it still, in that situation, it would still fail even if it were modeled as a solid, but the way that it fails is important, or I find much easier. So if cutting a part by a surface fails, it throws up an error. If cutting a solid by a solid fails, you end up with this weird orphaned piece of the instrument somewhere else that you can just tweak things and get rid of. Whereas the surface, it's liable to throw up kind of this vague, nondescript error that you spend 20 minutes searching on how to fix. Anyway, I hope you all have a great day. And if anyone actually stuck through to the end of this, I don't know, you all deserve a medal from the channel or something. But I do want to do some, like I said, some CAD streams about an Altoon coming up. And of course, stay tuned for more information about the subcontrabassoon. Have a good day.